Hello, how are you?
I'm good. How are you?
I'm good, thanks. Okay, so we're gonna do cooler stuff today. We're gonna get into concurrent programming starting this week. So if you wanna check out Canvas, and then I'll get your grades updated for this last week too, starting tomorrow and Thursday. Okay, so and then I will release the project probably in a few weeks. So I wanted to cover a big chunk of the project first, so that way it doesn't feel overwhelming when you look at it, okay? All right, so download the notes. I have it open, so I'm gonna go ahead and share. In your assignment, we'll go through them together. Not too much coding today. I think we're gonna do more of it with the lab. There is about one program that we're gonna do, a very simple program when we do the assignment today. Okay, so this is gonna be on chapter 6. And congratulations to Jimmy for winning the review game, right? Good job. Okay, so this week we're gonna start to get into the nitty-gritty part of Python that really makes Python more advantageous to, oh, you're welcome, to use in development. And so we're gonna talk about asynchronous programming, and that's really the big core in this class, is to look at asynchronous and parallel. So in chapter 6, you will find information on concurrency. And starting from this week, we are going to work with thread multiprocessing program, and then eventually we'll get into parallel programming. And then we'll talk about how to lock threads and create patterns when we get to the end of the class. So in asynchronous programming, it is a type of parallel programming. You would have different approaches on how you would write your program. And it's really depending on the goal of your program. So in web development, you would see that asynchronous programming is used. And so here it talks about asynchronous. So if you write a simple traditional Python program, right, it is synchronous, as your interpreter would read line by line, and it would interpret each line of your code and be able to give you the output. In asynchronous programming, we are going to work with the unit of work. And what we're going to do is we're going to utilize that to separate it from the primary thread of your application. So what happens is when you design your program, you want to divide up some of the subtasks or some of the areas that would utilize the resource, and we want to be more efficient. So we want to make sure that the timing and the use of the thread is incorporated appropriately. So a thread is basically a unit of work. And you probably hear about operating system or application uses multi-threads, right? Especially that we have the processor like Intel i7, i9 to be able to support that. And then when you write a multi-processing program, basically we can allocate processor to execute specific processes in the program. So it is slightly different than doing a multi-thread program, okay? So in your program, normally we would have a main thread, and we can subdivide that into many more threads, so that way we can handle all of that, right, to be able to reach the objective. So why are we really doing this? This is really to give more response in your program, also make your program perform better, especially when we deal with web-based applications or things that would be close to real-time or real-time. So we want to make sure that your web requests, like HTTP requests for your server end, things like that, needs to be addressed appropriately. So the example that they tell you here is for web requests, right? We are going to do some of that later on. So what we can do is in Python, we can use Async Io to really set up your coroutines, and we'll talk about what a coroutine is. So and if you're familiar with HTTP, so there are 4 parts when you access a website, right? Like this is my computer and I'm visiting a website. So what happened is the client system is gonna contact the server, and the web server needs to respond. It's gonna say, hey, are you that web server, right? And the web server is like, yes, I am, and I'm ready to receive your request. Then the client would contact the web server again and say, here is my request. And then the web server would respond and say, oh, I'm serving your request. So there are 4 parts in the communication. There's 2 requests, right? And then 2 reply. So with that, what we want to do is we can handle it this way. So in a synchronous program, in a traditional Python program, we can say, okay, there's request 1, response 1. There's request 2, response 2. So what happens is if you have a hang up in the response 1, none of the later parts is going to be addressed. So you might suffer in the delay if the response from the server doesn't reach back to the client. And so therefore, because it is all sequential, right? Therefore, you won't be able to get to the response to until a later time. Now, what happens when we do an asynchronous program? We can do request 1, send it, have it on queue, then work on preparing request 2, right? So we can have these 2 are concurrent. And then that way you would receive response 1 and response 2 at the same time. So as you know that when you have functions, right, what that is it's going to utilize the resource. So when we say resource, that would be RAM, CPU, storage. So what we can do is a lot of the time when you're looking at processes, we want to look at how the resources are used. And if it goes into queue, there is a little bit of a wait time, and we can capitalize on that wait time to submit the next task. So that way that it would look concurrent, but ultimately there is a pause, right, for the first. But in doing that pause, we can work on the next task. So that way the wait time is not a lot longer. We can shave off some time when we do asynchronous, and ultimately it's that. Okay, so this is what asynchronous would be visually in a flow. So for the synchronous model, right, what we can do is we can take the synchronous model, as we would see that the program would have a specific runtime, and we can break it up into the subtask. And we can see how that subtask can be divided into unit of work and making it pause in between. So let's say this is task is green, blue, and orange. So what we can do is we can start the green, right? And then start the blue, put the green on pause or on wait, right? And then start the blue during that time, then come back and finish up the green task, then put the orange on queue, so start the orange, and then finish out the blue. And that's how you do asynchronous, is that you would break it up into subunit of work and then be able to handle it. So in this case, the green actually have 2 threads, right? The blue has 2 threads and the orange have 2 threads. So we can start thread 1 and then put it on hold, then start the thread 1 for blue, then do the thread 2 for green, and so on. So you would be able to handle ultimately all your tasks asynchronously. Okay. So that's what it would visually look like. Now, when you work with asynchronous, you would have to pay attention to the resources. Okay. So in your system, these are the things that are going to handle your data, right? These are the storage container or location where your data exists. First, this is in registers, and registers are physically in your processor. So these are files or storage location inside your processor cache. Okay, and then we also have cache that are outside of your processor, sometime inside the processor, but just going to be connected, not directly inside the individual component. And if you're familiar with low-level programming like assembly, you worked with register before. So registers really handle machine instructions, right? And then cache is used, we talked about this before, where things get repeatedly used, it would have a storage location where it would revert back to that to retrieve the reusable data. And then your RAM, right, random access memory, that's on your RAM module or your RAM card. And then your disk drive, right, that could be your SSD or your HDD. So these are the locations where we can pull the data, or these are the container that store the data. And the data is used for the operation. So we have to think about where your data actually goes, how we would be able to retrieve the data when we develop our applications, and what would be more efficient in using the data. Okay, so coming back to the assignment now for number 1, it asks you to define asynchronous programming. Okay. And describe the purpose. So let me turn on captions and make sure. Okay. So asynchronous programming is parallel programming in which a unit of work is allowed to run separately from the primary thread, right? We want to separate that from our primary thread, because if the primary thread fails, then we don't have a full-blown application. We would have a delay in our application. Now, when the work is complete, then it would notify the main thread about the completion or the failure of the worker thread. So we would divide up into multi-thread, and outside of the main thread, we would have the worker threads. Okay, and later on, we're going to talk about thread pool, where you can create a pool of threads to represent these worker thread, which is just the subunit of work in your program. So a thread is just a subunit of work, and we would have the worker threads, right? And the worker thread will communicate with the main or the primary thread of your application. It is to improve your performance or the application performance and for responsiveness. Now, it is widely used to build responsive services and user interfaces. So when you're doing, could be web services on the back end or the front end, okay? That will be your user interface or for your server services. Any questions? As we mentioned a little earlier, right, you saw in the notes, there are 4 types of memory that's used by the processor for your system operation. So when it executes your program, it's going to go to the storage location to retrieve your data. And the locations are registers, cache, RAM, and storage. And storage, that's mainly your disk drive, right? Your HDD or your solid state drive. Now, why would a programmer manage your I/O device resources? So I/O stands for input and output. And a lot of things are I/O, right? Your disk drive is input output. We can store data to it. We output data, or we can go and retrieve the data from it. So that will be input. Same thing with RAM. The difference is that RAM requires power, right? So it is volatile. So if you shut your computer down, it flush. So this is more permanent. And then cache and registers, right? And the reason why would be that because the resources should be from I/O devices must be handled to prevent CPU waiting, right? So in order to address this, you have to handle the input and output. If it's not handled, then the processor will continue to wait, right? So it could be that a task that it needs to store the data, and if it's not being handled, then it's not going to move on to the next task. So if we can't store the data, therefore we cannot retrieve the data from where we store in order to output. Okay, so software, as I mentioned before, is really about how we place the data and how fast we can access the data. Okay. So the resources from the I/O devices must be handled so that way the CPU doesn't wait infinitely to operate tasks. Okay. So if you handle the input and if it utilize where it input or the data where it input to have the output, then it doesn't have to wait aimlessly. Any question? Okay, so let's come back to here, right? I put down some of the detailed information for register. Registers is located in the processor. It's used to execute machine instructions on low level. So if you do assembly programming, you often see this. And the data is accessed per clock cycle. So it is one clock cycle when it's accessing the register. For your cache, it is slower than the register. And it could be inside or outside the housing of the processor. So when you buy your processor like AMD or Intel, i7, i9, etc., it will tell you the size of cache that you would use for, or it would equip with that processor. So for the frequent operations and instructions and data, it would revert to cache. A lot of things we use are cache, and I think we touched on this before, right? When we talked about how we would create a cache area and be able to go back, especially like for recursive functions and such. RAM is slower than cache, right? And that's stored on your RAM module. It is going to be able to store more data. So for the applications that require heavy lifting, like 3D animations, a lot of the graphic-based applications, developer would revert to more RAM usage because those type of application require larger data sets, right? Container that would be larger container to store the data. And then you also gonna tap into your disk drive. It's gonna store the most data, and this is what you see with OS. It is slower than memory. It does require, right, more time as it is the slowest in transfer rate. So we have to think about where we want to place the data, depending on how fast we want to access specific data. Okay. And then for our answer, we can refer back to this. Now, I/O devices are much slower than the processor. So when you're looking at the benchmark speed for your CPU would handle, right, these storage locations at a lower transfer rate compared to the frequency that you see. So for example, I'm looking at like let's say the i7 processor, 11th generation, it might bench at 3.8 gigahertz, right? Keep in mind that that would be the optimal speed, right? Most of the time we would see that when it's pulling the data for operations or execution, it would be slower than that. And also you're tied to the speed for the storage too. So if you're using SATA or SATA 3, right, you're going to be tied to the disk, the hard disk drive speed, or your SSD if you're using the M.2, right, that will be the channel that it would be able to use to transfer your data. And then if you're looking at cache, so each of these there are restrictions on how fast they transfer the data based on the technology that's equipped to the location. Okay, the bus speed for RAM and also the RAM module, right? So you tie to the motherboard and such. So how can we do multiple things at once, right? An area that we can look at is to write a multiprocess program. So as we have CPU that would have processor or multi-core, we can see how we can share the resources across the processes, okay? And so that way we can execute them simultaneously. A second area that you can implement is your multi-thread. Okay, so writing a multi-process program is different than multi-thread program. So a thread, as we say, that it would be a unit of work, and that could be a line of execution. So you can have a thread pool or a group of threads that would be used for one process. So you can take a process and you can subdivide it into multi-threads because they share common resources. So what would we say about resources? That will be storage, processor, right? And so now it tells you here that it is difficult to write a threading code. And your OS does a lot of the heavy lifting by sharing your processor. So if you ever go to like Windows Task Manager, you would look at your processes, right? A process can take a long time. It can go into idle. It can wait, and it would finish out at a certain point, especially when you launch an application or you utilize an application. So in the operating system, what it's going to do is going to use GIL or Global Interpreter Lock. That allows only one thread to run in a Python code at a given time. So when you have multi-thread, what it's going to do is going to lock a thread, and that thread is going to run. And then we can go to the next thread. So we would use GIL in order to handle the multi-thread, because you cannot have 5 threads running at once, right? You would need to lock in on a thread that's going to run and then release that thread and then take on the next thread, right? It's going to pull from the group of threads, which is a container thread. So in C Python, GIL prevent multi-core concurrency, okay? So that means that even if you're running a single core, through that you might have 2 or more cores, what it's going to do is only going to see it and treat it as a single core. So how do we implement the multi-processes then? What we can do is we can dedicate 1 core per thread, okay? So when you have 2 or 4 more core, what you can do is you can lock in on 1 core to that specific thread, okay? And so that's how we can maximize on a multi-core concurrency, because GIL only sees 1 core at a time, okay? All right, any question? Now, the next part talks about you can also implement coroutines. And coroutines are just subroutines. They are used to do multitasking. And if you're familiar with subroutines, this is talked about in, or this discussed in like assembly programming and also Java, right? Subroutines are treated as functions, right? Or just the division of your functions. So they're just also tasks. So we can handle the coroutines for the multitasking, where we would do the voluntarily yield, which is the give away the control periodically. So in a similar concept where we can say, okay, it's gonna yield, right, or idle, so that way other coroutines can be handled simultaneously. Okay, so you can put it into a wait or an idle mode, and then be able to generate, right, additional methods to be able to handle the task. Okay, so you are going to have to implement the yield statement. And you're going to treat the coroutines as generator. And the generators is going to produce the data that's going to iterate. We talked a little bit about generator before. So it's going to produce the data that's going to iterate while the coroutines can consume the data. Okay, so it's going to overlap as we look at that. It's going to loop. So when we say iterate, right? So in order to produce the data, we just iterate. And so the coroutine can consume the data. So we are going to see how coroutines are written, right? And then we're going to also talk about event loop. Any question on this? So these are separate individual approach on how you can implement concurrent programming. You can make a multi-processing program, you can have multi-thread program, or you can implement coroutines. Okay, let's come back to the assignment now. So for number 3, it asks you to describe how coroutines are used for cooperative multitasking. So we can say that coroutines are generalized subroutines. They're used for cooperative multitasking where a process would voluntarily yield control periodically. We can put it into idle, okay? Or when idle, to enable multiple applications to run simultaneously. So when it goes into idle, other things can run during that time. And with that, we would shave off the time and improve performance. And for number 4, the main purpose in developing concurrent program is to prevent tasks from blocking each other, right? You saw at the beginning, if I have HTTP requests that never gets resolved, right, I won't be able to finish the later task, the later response. So in a synchronous program, that can happen. You can have something that delay the rest of your program. So in concurrent programming, we can implement the task and capitalize on how we can multitask to prevent blocking, right, the task in later part of our program. So here I say that concurrency prevents tasks from blocking each other by switching among them when one is forced to wait on the external resource. So in the case that if you're waiting for additional input from an external resource, could be a user striking a key on the keyboard, or another server communicating, or another service is initializing, right? You can put, right, some of the subtasks or other tasks onto queue and prepare and use the resource, so we are more efficient that way. Okay. So on the abstract level, what we can see is, to multitask, we can handle one thing, put other things to wait, come back, put the primary things on wait, and then handle the other things, right? So we're able to juggle multiple things at the same time through implementing, right, the wait time for various part of our task. Any question on this? Okay, so let's come back to here. And so you can get into the details here. I put down the goal for concurrency. We saw that in our answer. And so if the work is splitting up the task into subtasks, and those subtasks can be addressed as, with concurrency, it would partially advance without having to wait for the previous task to finish. So we are not blocking the rest of the application. And you would see this a lot of the times for applications that wait for network requests. And that could be a lot of different things. The easiest is for most people to visualize is to look at HTTP. Okay. And for example, I can visit a site, and I can, and through that, right, I would require a certain service. Okay. For encryption or authentication, or even download, access different things. So when you require a lot of different network service, what will happen is it's going to launch various requests and wait for the response to finish. Okay. But instead of waiting, doing, request, reply, like what we've seen before, we can submit one request, wait for the finish, but we're going to launch other requests at the same time while this is waiting, right? So we would put it on wait and then launch the other, come back and handle the reply, and then address the other requests. So that will give us concurrency in how we would approach that. And so when you look at it, it would be like this, right? And we would need to import time because we use that and the value that's passed to handle how that request is going to be on pause. So we would have a function or a method here, right? And then we would give it a return. So if it's successfully connected, right? Like if you have a web server, if it responds 200, then it's true. Then we would have the result and we would handle the number. So this is a simplified way, but when you use like HTTP package and stuff like that, it's slightly different. But as you can see here, if it's successfully connected to the web server, right, we would have the result, and let's say we would do some kind of operation. And there would be a pause for that. So we would put it for a wait time. And then we would do other things. We would go and fetch for other computation, right? So that means that we can initialize, or we can start the next part of our program by getting this, by preparing the next task here. So we would define the function. Your response is going to be, what was returned in the previous part here, your result. Pass the number. If the response is success, we're going to print, right? And then we simply call the next function here. So as you put the previous function on idle, right, on wait for 1 second or 1 microsecond, then what you can do is you can call on the next part. Okay. And so that means that it's gonna, and when we continue to call fetch square, right, and we would pass the value, you would still have the output. Okay. So that's how you can handle the primary task and then set up the next task on the queue. Okay. So when we visualize this, how does the CPU see this? Right? So the processor is going to look at what is submit the request, and that will be in orange. While it waits, right, that will be in blue. And then it's going to execute the fetch square, so it's going to compute for the next part here. So you would put the blue on wait, and then it's going to handle the orange task. Okay, and then it's going to come back and do the blue. So that overall reduced the wait time for the processor. Okay. So concurrency is really just the main goal in that is just to reduce the wait time. Now let's take a look at callbacks. So a call is responsible for the time sleep, which is our idle time, right? We put it to wait. We can start working on other tasks. So we need to really find a way to block it from the flow to the rest of your program. So remember that we would need to do the blocking, so it's going to only address that one specific task that we put it on queue. Okay. So in this function, what we're going to do is we are going to put a wait time. Okay. That allows the program to block the execution for 1 second. Okay. So you simply just implement the idle time here, and that's going to block the program from executing for that. It's going to pause it so the processor can handle other functions while it's pausing. So a callback is a function that can be called during when the wait time expires. So a callback, it's going to call after that wait time is up. Okay. So that means that we need to activate it when your timer starts. Okay. So here, as you can see, we define a wait to print async. And then inside that, we also define a callback, right? We are going to do your timer object here. That's going to use threading. This is a module. And it is instantiated for the timer class. Then we have to implement the timer start. So that's going to activate the method, right, for the callback. Any question? So on the abstract level, this is sometimes can be difficult to visualize, but once you start writing the program, you can see on how we can put things on pause and activate the timer so that way we can execute. Okay. So on a asynchronous program, this is how it would look like, right? We would wait to print, first call, second call, after call, and it's going to just handle one line at a time. But on an async program, right, it's going to put things on pause. We're going to wait for 1 second. And during that wait, right, we can handle other tasks. And then the callback is going to be activated after your time's up. That 1 second is up. Okay. So with that, we're going to answer the next one. Why is callback important in concurrency programming? Because it allows us to implement await, which allows the rest of the program to continue. So it puts that one function on pause and handle the rest without waiting for the beginning execution. Because in an asynchronous program, it's going to be top down. So if the top is not being handled, then it never gets to the bottom. So in a concurrency program, you can put the top part, right, to pause by implementing the time wait. Okay. And when that time is up, then that will be the callback. Then we can allow the rest of the program to continue. Any question? All right. No questions. So now we're going to talk about future. So let's define what future is first. So future is a pattern, and futures allows us to keep track of callbacks. Okay. So it's a way for us to track requested resources that we are waiting to become available, like CPU or storage. Okay. So a future is a tracking mechanism for requested resource. So in Python, we can implement future by using concurrent future class, right? Developer already created this for you, so you can tap into the resource. So it is an instance that created by calling the constructor with no arguments. Look like this. Okay, so you have FUT, this is the object, instantiated for future class. Okay, and what it will tell us here is that it's going to say that this is the location and the state it is pending. So you can use this to monitor the resources that are becoming available in your concurrent program, right? So it's telling you that the address for the physical location and the state. Okay. So if we use that to represent the value that is not yet available, that will be in the future, hence the name, right? That might be available soon, then we can implement the value, and in this case we pass a string. So we can say if you set result, pass the string, and it's going to tell you that this location and its state. Okay, so it's going to return the finish. It's finished and it's returning the string. Hello, as that is called. Okay, so it's just a way for us to track, right, what resource and its state that is becoming available. Here's a more full example. So you would use the import statement like this. From concurrent futures import future, then we would define our function for our network request. Inside that, we need to instantiate this object future, right? Because you want to implement futures in the program. Just like before, we have the state of your network connection. Then we implement the wait for the timing for our callback. But here we have to use the function call and pass it with the result inside, and we want to nest it inside the instantiated of the timer class object. Okay. Then we have the timer start, and we will return the future. So modifying the program from what we've seen before to implement future, you have to create the future object, right? And then you got to utilize or access access that object to be able to implement that with your function. And you want to pass that inside your threading for your time wait. So your idle time, you need to pass that as a parameter, okay, when you create the timer object. And you can also implement the framework with features, okay? So if you want to handle this with the framework, you can manage the features. So in this case, we saw how fetch square is used. You're still going to create an object for the future, right? And this object is going to contain the output from the other functions. Okay. Then we have another function defined. So when it's done, we're going to pass future. And for the response, we would access that object to get the result. Now compare this to the previous here, right? You only instantiate. So you need to instantiate the future here to be utilizing in this one. Okay, see how it passes future here? So when it's done, right, what it's going to do is going to implement the callback. So what this does is it's going to prepare the instance for upcoming operations. Okay. So all of these functions, all that is to be able to track the status of your upcoming operations. So you're going to see that there's going to be a wait. It's going to do the first call. It's going to pause, second call, and it's going to go to the after call. Then, right, so when it prints, you're going to see that it's going to print based on how you put it into pause. So when we put it into pause, what we can do is we can prepare, right, other calls. And we would use the future to track the resources for the other calls. And that's the whole purpose in this. Okay. So for 6, it asks you how is future used in a concurrent program. So first, you need to construct an object using the future class as what we would see future is, right? And we would leave the parameter empty. And we would use the object to keep track of the callbacks throughout the program. So as you look at the example, once you create that object called future using future class, you can implement it in the functions to track the callback in your program. Okay, so let me come back to here real quick. Let me go to chapter 6. Yeah, I don't have some of the code for, hold on 1 second. Let me see if I can find you some example. I don't think I'm able to retrieve it now, but I will share that when we look into the lab. Let me see. Yeah, that's the only one I have. So, okay. So when you compare your synchronous program to the asynchronous program, you can see that you do have to implement the timer. That's one element, right? Ultimately, in summary, what we need to do is we need to implement the timer to make sure that we would have the time start after the timer object here for your callbacks. And then with that, what we would see is when you implement the additional functions, okay, to be able to execute the task, what it's going to do is going to load the additional functions after the first part to your program while it's going to put this on the 1 second wait. Then what we can do is we can add in the future to track, right, where the resource is accessing for each of the call. Okay, because as it gets to when it loads the 2, when it execute this and it finish, right, we would be able to see that. And then for 3 and 4 and so on. So as it executes the call, what you're going to see is you are going to see how this resource is utilized while we're putting the pause. Okay, so future is just a way that we would track the resource, what's being used for while we're implementing the wait time for concurrency. Another area that we can utilize is event loop. And event loop also allows us to monitor status of your resources, very similar to what you've seen with futures. So we can implement that for database queries, network connectivity, anything that would be triggered by the callback execution. Okay. So loops can then be preferred over threading because it is simplified how you implement your data structure in event loops. Okay, so in development, event loops is probably more preferred. Okay. So basically, it's a way for us to check the status. Now, you don't want database queries to hang forever, right? So that means that we can look at the time on for that specific task, like database query or network connectivity. So here, what you can see is we've seen this before where we start, right? And what we can do is we can see if it is greater than the timeout. So instead of subtracting to see the difference, you're going to take the return time, subtract, and you want to check to see if it is greater than the timeout because you don't want that to exceed the timeout. Okay. So we can implement it to check the timer status. And so we can add in a while loop because here's our timer object. So we pass it with the 1 second. While it's true, if timer is done, right, it would notify us and then we would break from the loop. So why do we need to do this? So for the program that will do the work while the loop is taking place, so when this is taking place, we can prevent the execution block so that way the program can go and do other tasks. Okay. Now, because it's a while loop, right, as long as it's true, right, it's going to continue. And then when we break, then we would start from the beginning again. So we can wait for even to happen by the continuous poll for the loop. So it's going to show that it is busy waiting. Okay. So here, if we implement the callback, with the timer inside our while loop, this will allow our event to have the callback. Okay. So callback takes place when that timer is done, right? And then you can add in more timers. You can have it wait 1 second, 2 seconds, and then you can append. So really the event loop is to work with the time and implement a loop to check the time. Okay. So when that loop happens, it's able to execute other things. Now here it talks about the restriction is that the flow of execution is managed depending on the loop. So if it is continuously running loop, it never uses the blocking call. So you can let an event loop to use to detect and execute the callback for the resources ready. So basically event loop is useful to check the status, to check the resources. So when the resources is ready, you will be able to come back to your primary program and be able to execute that. Okay. So let's answer the next part. How is an event loop implemented in a concurrent program? We would use an event loop to pull the status of the event while allowing other tasks to be executed. A while loop can be implemented with the callback, and that's how you would add. You can look at the example on how you would implement a loop to pull your event. Okay. We would check the time, and if you add the callback in there, right, that will give you the status of that event. Any question? So throughout this week, we are going to work with Async Io. This is the library that we're going to implement for Python. In the future week, we are going to tap into other libraries as we look at how we can expand on parallel programming. Okay. So an Async Io is a library that's used for asynchronous programming using input-output. So for question 8, ask you what type of library would be used to implement concurrency in Python programming. One of the options is Async Io, and that's the main objective for this chapter. Okay, let's look at some additional things before we start writing the next program, just number 9. So Async Io, right, is used for concurrent code. This allows us to do asynchronous programming and await syntax. So these are the things, the elements that we can implement from Async Io. It is used as a foundation for asynchronous framework for high performance. So when you write program for networks, web servers, databases, you should use Async Io. Or things that are for distributed task queues, or any type of IO bound or high-level structured network code. So you often see Async Io. You can also implement high-level APIs. And through Async Io, we talked about how we can add in coroutines. So you can implement coroutines in your program. You can use this to control subprocesses and divide up tasks for queues. Okay. Now on the low-level API that is also supported, you can use event loops for the low-level APIs. You can use it to handle operating system signals, subprocesses, protocol transport, and so on. So Async Io is often used for networks, right, or network communication. And you can access the link to look at the library. So when you look at the example, we can simply import in the package or the module from the package. And then when you define the function, you just have to say async, okay, from Async Io. That's the keyword, the syntax. That's what they talked about earlier. You can also use await to pause. So we would say async, and then we would define our function. And then await. So these are the two keywords that you can implement from this library. So in this function, we just call it main, and then we want to print a string. And then we would make it sleep for 1 second or pause. And then after that, to do that, we would then handle the will. Okay. So to call that function, you have to say async io dot run, and then your function inside the parameter here. And this is from their documentation. Here's your book example. Okay. You have the import statement. And you have loop is going to get the event loop. So it's going to use this function or this method from the library. We define a function called callback. In that we would print hello async io. Then we would stop. Okay. Then we would have the call later method, and we would use the pause here. And we would pass the callback inside this parameter. And then you can use additional function like run forever. So it's going to keep going. So the way that the book uses, they implemented a lot of the built-in function from the library to be able to make it run, make it stop, make it go forever, or make it go on wait. Okay. But ultimately, if you refer to the documentation, you can see that we can use async and await like this, right? But you can, in order to execute, you have to tell it to run. Okay. All right. So looking at those examples, we're going to do the next one. So look at the documentation. We are going to write an asynchronous program that's going to display 2 strings. You can put any 2 strings you want. Okay. So here is my program, and I will run it in Tawny so you can see. So the first line, I wanted to import Async Io, and as I do this, make sure that my IDE have that package, okay? So you need to make sure that you find Async Io on your IDE and install it. And then I'm gonna define my function called greet. So I would say async, right? And then define my function. And then like the example, I'm going to do a print welcome. And then I'm going to make it pause. So I would say await async io sleep, and I'm going to give it 1 second. And for the await, I'm going to print hello. And then to run the greet function, I would say async io dot run. And then for its parameter, for the argument for run, I would then pass greet as the function call. Okay. So it's going to execute this function by using the run method from the library. So with that, we met the objective that we are displaying toString. In that, right, we define a function using async keyword. And also we put it on pause by using await. This reduces the extra stuff that you need to do with time module, right? Or time it module. So you can do it, the other way where you would add the time start, the time pause. You can just put it to wait. But await allows us to use the library to pause, to make it sleep for 1 second. Any question? Okay, so let's come back to here. So on Tani, don't forget, or on your IDE, don't forget to add your package. So we want to make sure that. And keep in mind that Python version 3.7 later is supported by this library, as you see that in the documentation. So if you're using an earlier one, you have to upgrade your Python versions. Okay. And then, once you find the package, you can just click install. I already have it installed. Okay. And so here's my program. Then I'm going to print. And so as you can see, right, it does have the pause. The reason why that we implemented the pause here is we want to access the resources for the next part. Okay. And so when we print, we just wanted to see how that's going to flow. So it does implement the 1 second wait. And so it's about like using that time to access the resource. Now, in this, we're not adding threads or we're not using any additional things. So we just we don't have additional subtasks to handle. You will see some of that later on. Okay. But that's how you can use the module to be able to implement the wait time. Any question? Okay. So that was 9. So now we are going to go to the coroutines part. So we said before, right, coroutines can be implemented for our concurrent program. In this section, it talks about how we can use yield. So this is a way that we can break up the program execution into small parts. And then that way, it's gonna let you handle other parts of the program while it's yielding. Okay. So when we implemented coroutines, it will be like this. You can define your function. Let's say that you have a loop, a while loop in that function. We can say while I is less than n, we're going to print the generated value, and we can format it. Okay, and we can move through the value of I by incrementing 1. So we add in the yield I here. Okay. So when you look at the documentation, Async Io does support coroutine. And we can implement the coroutines by using yield, or in this case, we can also make it await. So there are 2 ways that you can do that. Okay. You can do it like the book way where they implemented the yield statement, or in the documentation, right? They use await for the coroutine. So in this code, what we're going to do is we are going to print hello after waiting 1 second, and then print world after waiting 2 seconds. Okay, so we implement the pause. So just like before, you define a function. In that, you're going to set up the delay. So we are going to wait, right, for the hello. So it's going to sleep there, and then it's going to print hello. So wait 1 second. Then for the next part, it's going to wait 2 seconds. We're going to pass 2 for the world. Okay. And just like before, we just use the Async Io run to execute main. So here it shows you the time as they format the time to show. So you can use this way to test, or if you wanted to use like the way the book shows you, you can implement the yield statement. Okay, so that's like 2 approaches that you can use. So ultimately, when we implemented coroutines, you need to implement some kind of pause, and we can use await or mute. And in this one, there is a function that comes with the module to allow you to create tasks. So here I have task 1 that instantiate the object as task 1. Okay. And for that, I can tell it to wait 1 second and say hello. For task 2, you can use create task to create the task, and that's gonna allows us to print world. Okay. So defining this way allows you to use the create task function. And then we just have it to do await task 1 and task 2. And it's still going to show the same thing. Okay. So here we can say that for number 10, it says, what happens when we call the coroutines up 9 in shell, right? When we implement the coroutine, it's going to contain the memory location of the coroutine object. Okay. So if we implemented the coroutine, we can use it to really track and see, right, where it stores the resource, or it's going to refer to the resource or the storage for our task, which is our function. So how can I execute the coroutine? We saw that you can use Async Io run, right? We did that in this program. And in that, we would implement await under coroutine using await statement and the value that you want to pass for it to wait. You can also implement Async Io create task function. And with that, you can also use await. With its parameter for the pause. Okay. And then you can also use yield statement with wait time. So there are several ways that you can implement coroutine in using Async Io. Any question? So to execute, we would use the run, but before that, we can instantiate the task and then make it wait depending on how many that you want and how long that you want for the resource to become available for others. Okay. Okay. So the next part we're going to talk about is your awaitable objects. So the object that is waiting, we can say that those are awaitable objects. And so when you use this with API, it would use awaitables. Okay. So there are 3 types of awaitable objects: your coroutines, your tasks, and your futures. And we talked about the coroutines and the futures. Tasks, we're going to see more of this when we're looking at multiprocessing. So when you write a coroutine function, you simply use async def and then your function name. For your coroutine object, you just define the object that's going to be returning the call of your coroutine function. You saw that in the example. Your task is going to be used to schedule the coroutines concurrently. So these are the type of awaitable objects in a concurrent program. Okay. So we define the function, right? That's this part right here. We create the coroutine by using create task and await task. Okay. So you can set up your task on when you want it to run. So you can have it await and then the task to be executed. Okay. So you create the task and then you can have it paused to when you want it to be executed. All right, for future, we talked a little bit about this. This is low-level awaitable objects. This is also an awaitable object. Okay, so that just means that this object is awaited. So the coroutine will wait until the future is resolved. Now, this is needed to allow callback using async and await. So this is how you can implement futures. So you define the function using Async Io, right? Or async from Async Io, and then you would await for the future. And then we can implement gather method. So we can pass the function to return the future object inside gather. And then the coroutines. Okay. Now, when you implement thread for the operating system, OS handle most of the thread part, right? And when we want to do parallel execution of the blocking code, you can implement thread at the OS level. So the purpose in this is to run the task separately as individual thread and monitor the progress or their state using future. So when you write a multi-thread program, it's probably best to implement futures So that way you can monitor the state of each thread. And so through the libraries, you can spawn or create a group of threads called, we know this as workers, but we're going to see this as a pool thread. So you can spawn a collection of thread and let them wait, right? You can put them on pause and be able to handle various threads. You don't have to go from 1 through 5, for example. You can go 1, 3, 2, 8, etc. So threads can be handled and monitored individually, right? But we just need to implement features to be able to track them. Track the workers. Okay. So it would show like what's pending, what's finished, what is done based on your collection of threads. So on here, you see, this is a request module. I work with this when I teach cybersecurity for Python or networking. This shows you how you can connect to web servers, okay? And this example shows you how you can do that using Async Io. So we would import Async Io, we would import requests, we would have it go and fetch the URL. And then as the server respond, we would have it stored into a list. So implementing the for loop, we would append and using that to do the request get, and this is part of the request library. So it's gonna go and based on this, it's gonna have a list of URL, right? It's gonna fetch the URL and then submit it. It's like how you type in your browser, like one URL after the next. So why do we need to do this? We can test our web servers this way. You might have multiple web servers. You see if it's going to be responding when it's connecting to different web servers. Okay. So based on this, it's going to go to google.com, example.com, facebook.com, and the response is going to be stored onto the list and we can have it printed out. Okay. So what you see here is this example allows us to implement await, right? So when it's submitting the request for one, it's going to queue the next one, right? So if it's submitting for google.com, waiting for the response, it's going to go to the next step and it's going to prepare example.com, get that ready, right? Work on that, then come back to google.com and then append the result. Go here, look for the response from example.com, append the result while it's putting facebook.com request, the first request in place. Okay. And this is not the only way you can do this for database queries and so on, because you might have thousands and thousands of database queries. So this is just a simple example of how you can implement that. Okay. Any questions? All right. So for the last part, we're going to talk about reactive programming. And as we mentioned, that a lot of these things that we're learning, this is needed for applications that require more responsive, real-time response, and so on. So there is RxPy, which is a library that can be used for reactive programming. And this is often implemented for concurrent system or concurrent applications. Now, these are the requirements when you are doing reactive programming, okay? It needs to be responsive. So that means that it needs to have immediate response to the user. So no wait time or delay. It needs to be elastic. It is capable of handling low or high load. of demands. And so a lot of the time web and cloud is it falls into this area. It needs to be resilient. That means that it needs to be able to adapt. And so you would have modularity and you don't have a single point failure, meaning that if one thing's failed, the rest fail. So you want to have it all broken up into subpart. And it needs to be message driven. So the system should not block or take advantage of the events and messages. Okay, so message driven application is going to be fulfilling all of these. Okay. So in the last part of our assignment, we can say that what type of libraries are used to compose asynchronous and event-based programs using observable sequence, pipeable query, operators, Python. How do you install the extension? And we're going to see this in the lab. You are going to use reactive extension for Python. It's called RxPy. Okay. So in your IDE, we will talk about this in our lab as well. When you install, if you type in Rx to search, you're going to see that there is reactive extension for Python here, right? But if you do RxPy like this, it is regular expression, so do not mix them up. Okay, so regular expression is RxPy, where Rx is your reactive extension, and this is the one that we're using. Okay. So for this answer, we can say that we are going to install or use the reactive extension for Python. You can just put Rx. And then to install it through command line, you would say pip3 install Rx. You can bring it in from your IDE. And this is the confusing part, is because in the documentation it's actually RxPy, but the package is Rx. And then when you search for RxPy as a package, it is a different thing. Okay, but it is known as your RxPy operators. So for 13, it asks you to describe the purpose of RxPy operators. This is used to create, transform, filter group of observables. Okay. And we talked a little bit about observables earlier. And so how can you create observables using RxPy? You would use a method called observable.from_iterable. And that's going to come from your RxPy extension. So after this, the lab for this week, you are going to see how for your reactive extension is going to be implemented with Python. And this is for highly responsive applications. Okay. A lot of time network service-based, database, distributed systems type of environment. Any questions? Okay, so that will be the end of our assignment for today. I encourage you to take a look at the documentation, the example. That's going to give you a little bit more exposure to this. because from here on out, the concept is a little harder than what we've seen, right? And in this class, every week, you're gonna tap into something that's gonna add to performance improvement. So, but in the project for this class, you will be required to do a parallel program, utilizing at least one of the module, and there are different options in this class, so you will need to implement, and depending on the module you use, you need to be able to handle it. So if you're using, if you're using Async Io, I would expect you to have, if you implement that with threads, then I would expect you to have thread pool, using await or some kind of element that you can implement, coroutines and other things. Okay. All right, let me stop recording.